Okay, welcome. This is video 3, or I guess 4, since the first one was 2 parts. This is Unit 1, Section 3, Rates of Change and Behavior of Graphs. So finding the average rate of change of a function. The average rate of change. What on earth is that? You may have heard that as the slope. They're the same thing. It's the average rate of change in y as you move 1 unit in x. So the change in y as you move 1 unit in x. It's always forward 1 unit in x. You're always moving forward. So if you were to say, well, what is the average rate of change? Well, if it's the slope, then we know that that's going to be y2 minus y1 over x2 minus x1. So what that means is that it is the change in, and it's this weird triangle with a shadow. And this is called delta. So it's read change in y over change in x, or delta y over delta x. And they mean these things, these guys. So that's the change in output over the change in input. And the formal definition of the average rate of change would be this. The average rate of change between 2 input values is the total change of the function values divided by the change in the input values. So output over input. So what it's saying. And these are equal to y. Right? So we can find the average rate of change if we're just given 2 values. So if we have, we know that this is 1 point and this is 1 point, then our average rate of change, our delta y, our delta x, would give us 2 minus 1 over 3 minus 2. So that gives us 1 over 1 is 1. So that's the average rate of change there is 1. You could do it from a graph. So if we were given a graph, I would just pick 2 x points where it's reasonable for me to see, and you would just count the number of y's they go down as you go over in your x's, and then you can just put that number that the y changed over the number that the x changed. You could also do the same thing from a table. If this is x and this is y, 2, 3, 4, 5, 6, 7, 8, 9. You could take your point as 2, 6 or 3, 7, or you could any combination of them. Doesn't matter. And that's how you could do that from a table. So this is an example of using a formula. So the electrostatic force measured in newtons, it's F, between 2 charged particles can be related to the distance between the particles, that's D, in centimeters by this formula. Find the average rate of change of force if the distance between the particles is increased from 2 centimeters to 6 centimeters. So our D1 is 2 centimeters. Our D2 is 6 centimeters. So I want the average rate of change of the force if the distance moves. So that's going to be the change in the output over the change in the input. And that's a nice way to think about it, you know, especially when you kind of have no idea what's going on. So we know we have a formula. And what is our input? Well, it looks like our input is going to be D. So then that's going to mean I have to have my change in D on the bottom. And what's my output? That's F of D. So I'm going to have that change in the top. Now, my change in D is going to be 6 minus 2, right? Because that's D2 minus D1. And my change in F is going to be F D2 minus F D1, right? These guys on the bottom are D2 minus D1. They've got to stay in that order. So keeping that in mind, F of D2, D2 is 6. So we have 2 divided by 6 squared. It's 2 divided by 36. F of D1, D1 is 2. 2 divided by 2 squared is 2 divided by 4. So now we're going to have 2 divided by 36, which is FD2, and FD1 is 2/4 divided by 6 minus 2. So now we need to deal with these fractions. So I guess we can start listing multiples. 4 is 4, 8, 16, 20, 24, 28, 36. 1, 2, 3, 4. It's 9. That's a bit of scratch work there for you guys. And that's what you guys pretty much should be going through if you kind of don't know where to start. So that means that I can multiply 2 over 4, both of them by 9. I'm going to go ahead and do 6 minus 2. Okay. So that gives me 2 minus 18. That is going to be negative 11. No. Negative 6. Divided by 36. Divided by 4. So now what am I going to do about this 4 in the bottom? Well, it essentially is a fraction, of course. So negative 16 divided by 36 times 1/4. And I know this is 4 times 4. If this is boring, I know it's tedious, but I'm trying to show every step here because somebody might not understand where I'm getting something. So bear with me or fast forward. Minus perfect. So what that says is the average rate of change of force as the distance changes is negative 1/9. And now we're going to have another example. So find the average rate of change of this on the interval 0a. So we know we're going to have the average rate, the change in the output, that's right, over the change in the input, delta output over delta input. So my input is t, so that's going to give me t2 minus t1. My output is g of t. G of t2 minus g of t1. So now you might say, well, what's g of t2? I know here that t2 is a and t1 is 0. So t2 is a. And everywhere where there was a t, I'm now going to put an a. And my g of 0 is 0 squared plus 3 times 0 plus 1. And that gives me 0 plus 0 plus 1, which gives me 1. Okay. So my g of t2, my t2 is a, my t1 is 0. Remember, my t2 is a and my t1 is 0. That's going to give me a squared plus 3a plus 1, which is ga, minus g of 0, which is 1, divided by a, because this doesn't really mean anything. These obviously cancel out, so we are going to have a squared plus 3a divided by a. Well, looks like we can also cancel out an a, right? Because if we take this a out, that's this factored. Notice they're the same thing. Then we get a plus 3. And that's it. Your average rate of change on the interval 0a is a plus 3. So that means whatever you make your interval, you're going to add 3. So if it were 0 to 4, it'd be 4 plus 3 would be your average rate of change. If it was 0 to 20 billion, it'd be 20 billion plus 3 would be your average rate of change. And that's the beauty of generalizing with the alphabet. So, using a graph to determine where a function is increasing, decreasing, or constant. Okay, we're still good. So what that means is if you have a graph, that's our graph, right? So what color should we have? Here we go. So now if we were going to be talking about increasing, things that are increasing, we're going to now be talking about points on the graph where you can see things are increasing, getting larger, right? So things are going uphill. And these correspond to intervals down here. Right here. So the y is getting larger in these intervals of x. And then we can see for decreasing, it's where things are kind of going downhill. That means that on these intervals, you've got your y's decreasing. I'll just keep it there. Now, there are no points on this graph that are constant, but sometimes you will see graphs, I'll do a little example graph, that might look like this. This little bit in here, that's constant. That's what that means. So that would mean for these values of x, your y is constant. Now, local minima and local maxima. So an increasing function, we talked about where it was increasing, talked about where it was decreasing previously. So a local maximum is the point where it goes from increasing to decreasing. This is your maximum, right? Because if you have a maximum on a graph, it's going to be increasing and then it's going to be decreasing. Now, if we're talking about minimum, it will be decreasing and then it will be increasing. Okay. Right here, so it'll be decreasing and then increasing. So what this says is that x, for when it's increasing, it's a local maximum. X is x2 is greater than x1, and f, so if x2 is greater than f1, f of x2, if you choose a next point over, so x2 being, this is being the max, if you choose that next point over, then it will be less than f of x1. And what this says is x2 is going to be greater than x1, so that's our max. So we're going to choose a point right on the other side, or right on the other side of the minimum. Right? Like that. So this is x1, this is x2. And that says f of x2 is greater than f of x1. So that's how you should think about things like this if you want to think about them in terms of functions, using function notation. And I believe we're going to an example. Yes. Graph the function f of x equals x cubed minus 6x squared minus 15x plus 20 to estimate the local extrema of the function. Use these to determine the intervals on which the function is increasing and decreasing. So I guess your first question is, do I expect you to graph this by hand? Absolutely not. That's ridiculous, is it not? That's ridiculous. I couldn't do that by hand, really. I mean, it would take a while, you know, determining all of that stuff. Yeah, I'm not going to graph that by hand. So I did go to Desmos.com, and I already graphed it. So we need to use this to determine the intervals on which it is increasing and which it is decreasing. So since it's such a weird equation, I'm not going to be able to get the intervals quite exact, so we're just going to guess here. So if this is -2, that must be -1. So I'm going to say right here is a maximum. So that's going to be dividing one of my increasing and decreasing intervals. And then I notice here, which must be 5, is the minimum, which is also dividing my intervals. Notice. So this right here is an increasing interval, right? As x is getting larger, my y is getting larger. And here, as x is getting larger, my y is getting larger. So that looks like that's going to go, it's just going to go off forever. So I'm going to say from -infinity to, we'll go with -1. It is increasing on this interval, and I'm going to union that with the other interval. And I'm not going to include that minimum and maximum point, since technically at that exact point it's kind of really not doing anything. And then that's going to leave me with 5 infinity. This is when it is increasing. Now I'll need some room. I'm going to go to decreasing. Don't want to squish it at the bottom. Notice I only have one interval that it's decreasing on. It's this one right here. And it's decreasing on the interval -1 to 5. And that's how you would solve a problem like that. So let's see what, okay, I am going to go ahead and leave this up to video 2, because we're going to analyze these functions for increasing and decreasing. And I will see you in the next one.